Hey folks, how's it going? It is Mr. Murray coming to you with a video on absolute value functions and equations. And I thought I would record this through Zoom so you could see me and you could also see the work at the same time. So in this video, what I'm going to do is I'm going to actually walk through what is an absolute value function. And I'm going to walk through a couple of example graphs. So we'll look at the concepts, the definitions, and we're actually going to go ahead and take a look at some graphs. This is meant to accompany what you guys are going to be doing today. And so I really hope you find it to be a good, nice introduction to absolute value. And then as we proceed, right, this is really just the beginning. We'll work on some practice. All right. So as we discussed in class, what is a number's absolute value? So fundamentally, a number's absolute value, when we look at, and this is how it's written, right? A number's absolute value represents the distance. And usually we've learned that it's the distance from 0. But if you have something like x minus a, which we're going to see examples of that is the distance between x and some other number a. So it doesn't have to be between the distance from 0. When you first learned about it, that's what you most likely learned. And how do we know the absolute value of -5 is 5? Is that -5 is 5 units away from 0. And again, we have discussed this in class. All right, so what is the absolute value of 5? The absolute value of 5 is 5. It's 5 units away from 0. The absolute value of -10 is 10. It is 10 units away from 0. And the absolute value of 0 is 0. And one thing we talked about is that we know that absolute value refers to distance. So we talked about another idea, which we're going to revisit at some point, where I asked, what numbers have an absolute value of 5? In other words, what number x, and let me just back that up because I was just having a little bit of issues for whatever reason with my pen. So in class, we asked, what numbers have an absolute value of 5? What numbers? And we talked about how now we know there's two of them. One of them is 5, and one of them is -5. Okay, but then we said, what numbers have an absolute value that is -10? And we said none of them, because absolute value is distance, and distance cannot be negative. And lastly, what numbers have an absolute value of 0? Only one number, and that is 0. Okay, but that is absolute value equations. Again, that's something we're going to eventually take a look at, but that's going to happen more down the line. All right, next thing, how do you know the absolute value of 3 and -3 are the same? We said that both are 3 units away from 0. And finally, what kind of numbers can you get when you take a number's absolute value? That is, what numbers can be used when speaking of absolute value? And we said there's two numbers: positive numbers and 0. Okay, only positive numbers and 0. And again, that's getting to the idea that absolute value represents distance, and because distance, there's negative distance, doesn't make sense. You have to have a distance at 0, meaning no units away, or some positive number. Again, you cannot have a negative distance. Okay, and so that's going to help us when we get into equations, because if we find out that there's some kind of negative distance, that's going to be bad because we know that's not possible. And so the idea is we're going to have to, as I noted in class, look for scenarios in which there could be 0 solutions, 1 solution, or 2 solutions. So let's dive into what is an absolute value function. And an absolute value function is defined as f of x equals x. That's the parent function. So every absolute value function is a transformation of this function. And x is defined as follows: the absolute value of x. It's a piecewise defined function where it's equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So in other words, if the number that you plug in is greater than 0 or equal to 0, the same number comes out. So if you plug in 5, you get 5, right? As we saw. If you plug in 3, you get 3 because 3 is a positive number. If you plug in 13, you get 13. And also there's a special property that if you were to plug in 0, you would also get 0, okay? Because this is the numbers that are greater than or equal to 0. So in that case, 0 counts. But if you were to plug in a negative number, like -5, you would get its opposite. So -5 would give you 5. So that's just like the piecewise defined function. But the idea is, again, the parent function is just the distance away from 0. The general form looks something like this, okay? And this is going to have some things we might have seen before. F of x is equal to a times the absolute value of x minus h plus k. And the significance of hk is that hk is what we call the vertex. And the vertex represents the highest or lowest point, depending on what a is. So if a is greater than 0, the vertex, it's a maximum. I'm sorry, it is a minimum. Sometimes we get those flipped around. Minimum. And if a is less than 0, it is a maximum. So you can think about it as happy face, sad face. A is positive, happy, points up. A is negative, sad, points down. Now the h and k are very significant because when we looked at point slope form, we talked about m y minus k equals m times x minus h. And hk was a point on the line. Similarly here, hk is a very important point on the graph of the function. And also we have, we're going to see it if we, when you guys look at quadratics, we might look at that this year with the parabolas. You're going to find that there's a form of a quadratic function that's almost exactly the same as it. I'm going to show you what that looks like really quick. A times, notice what I do if I put it in parentheses, squared plus k. Now this is a quadratic function. It makes a parabola when you graph it, and hk is the vertex, it turns out, of that parabola. So why I've been focusing on hk all year is because hk has a lot of overlap where you see it coming up in a linear function, in a absolute value function, eventually in a quadratic function. You're going to see it come up in a square root or a cube root function, and it's going to play a very, very similar role. And we saw it come up in exponential function as well. And so that's what I've been focusing on hk, is for you all to see the similarity, the role that hk plays over and over. And as we're going to see, the a value here plays a similar role as well. So here's an example formula. Okay, there's many different possible examples. I'm just going to choose one. And of course, for whatever reason, my marker sometimes does not want to be my friend. Let's try that again. So all right. So sometimes my trackpad wants to do whatever it wants. So f of x equals, I'm going to do just straight up absolute value of x minus 1 plus 2. So what's important to note is 0 is like a really magic number. So remember, I think when we talked about graphing, make the exponent 0 when we talked about graphing exponentials, because we knew anything to the 0 was 1. We're going to do the same thing. We're going to make, and so this is going to be the same graph. We're going to make x equal to 1 because it makes the bars equal to 0. So when we do 1 minus 1 in bars plus 2, this becomes 0 plus 2. And the absolute value of 0, we know, we talked about that, is 0. So you can see you get the point 2. 1, 2. So the key here is to find the vertex, make the bars 0. Okay? And what this is going to end up looking like is something that goes up like this. Notice that after the vertex, you get the slope of 1. okay? Whereas to the right of the vertex, as you go from left to right, you're going to have a slope of -1. And notice how what number is in front of the bars? 1. So again, a very similar connection. Now in quadratics, it's not going to be exactly the same, but it's going to be pretty similar. Okay, so this is our absolute value function. If need be, please feel free to rewind and take a look at anything I talked about. And then what we're going to do is we're going to go ahead and move on. All right, so what we're going to do is we're going to take a look at 4 examples of absolute value functions. Some of these might be ones that I'll do straight out. Some of these might be ones I'm going to ask you to help me with as well. And I noticed that some of this might be a little bit cut off, and that's okay. We'll make this like a little bar. If that's cut off in your notes, that's okay as well. Not to worry. All right, so let's plug in the absolute value of -2. So I plug it in for x, I get f of -2 equals the absolute value of -2. 2 is how far away from 0? -2, that is 2 away from 0. I plug in -1, absolute value of -1. -1 is 1 away from 0, 1. I plug in 0. 0 is 0 away from 0. And then I plug in 1, and 1 is 1 away from 0. So it becomes a 1. So I plot my points. And what is the thing about graphing absolute value is it's the same as graphing any function. You plug numbers in, you see what comes out. That's how you get your points. So 1, 1, 1, -1, 1, -2, 2. And then again, you want to make this really nice V. Once you see the way you're going, the slope is going to be constant on the left and the right. So it's kind of like 2 different lines combined. And you saw that, right? Remember how we said it was x when it was more than 0? Well, what is y equals x? Slope of 0, slope of 1, intercept of 0. Similarly, what's -x? Slope of -1, intercept of 0, okay? So you can see this is y equals x. This is y equals -x, right? And it's pieces. It's a piece of y equals x and a piece of y equals -x. All right, in the next one, what are we going to do? So first we're going to plug in -3, and we're going to get -3 plus 2 in the bars. That's -1 in the bars. So that is going to be absolute value of -1. That's 1. Okay, then the next one, we're going to do -2 plus 2. Now notice what happens when we plug in -2. We get 0 in the bars. That is going to be a sign that you've reached a vertex. So remember, when you have 0 in the bars, 0 in the bars, that is when you know you're going to have the vertex. Because remember, the vertex means the highest or the lowest, and it's all based on the bars. What is the small? Remember, absolute value can't be negative because it's distance. But what can absolute value be? It can be a positive number. It can be 0. So the maximum or the minimum occurs when you have the smallest possible number coming out of an absolute value. And what's the smallest number that an absolute value can be? Is 0, right? The absolute value can be positive. It can be 0, but it can't be negative. So making the absolute value bar 0 is going to be really, really important to really making sure that you're able to excel whenever you're graphing an absolute value function. All right, now I'm going to plug in -1. So I'm going to do -1 plus 2. -1 plus 2 is +1. The absolute value of 1 is 1. Notice you also have this really nice symmetry, and we're going to talk about that as well at some point. And then I'm going to plug in 0. 0 plus 2 in the bars. That ends up being the absolute value of 2, which is 2. So I've got -2, 0. I'm going to actually graph this in red so we can look at something in a second. -2, 0. -1, 1. 0, 2. And it's going to look something like this. And I'm going to cheat a little bit. I'm going to use my, but I'm going to put an arrow on the end. I'm going to use my Smart Notebook to help me out. Connect that, it should make this little V shape right here. Again, arrows on the end because it will continue to go on forever, right? All these graphs go on forever. So eventually when we think about analysis, what is the domain? The domain is negative infinity to infinity. You can plug whatever number you want. Is the range negative infinity? No. And that's due to the fact that negative numbers are not going to end up coming out at this absolute value because the distance is never going to be equal to 0. Can you sometimes get negatives? Sure. Depending on the A and depending on the K value, you could get negatives. In this case, we can see we're not going to get negatives. So this is another situation like an exponential function where the domain is everything, but the range is not. And by having a graph, you can see what the range is. All right, other thing I want to take a look at is this. I'm going to go ahead and I'm going to slide this graph up, this red graph, and I'm going to slide it up so you can see where it would be if I'd graphed it along with the blue graph. What do we notice? The red graph is 2 to the left of the blue graph. Notice, where do we see a 2 in the formula? Okay, there's a 2 right here. So remember when we had exponentials, when we had a positive k and moved the parent function to the left, instead of, remember that was the one that worked opposite? Same thing happens here. When you have a positive 2 or a positive number, a positive h, inside the bars, that's going to move things to the left. So again, one thing we want to do is we want to see the commonalities. We want to see where the patterns overlap between different kinds of functions. Because if you can identify those patterns, then you can see what these different functions have in common, and that really drops the barriers that can often make plotting these different kinds of functions intimidating. So I, again, really start to think about the common patterns here. So if we think about the exponential function, we look at this one. What did the k do here? Well, usually it affected the asymptote. It moved the asymptote up or down. I wonder if it's going to have the same thing here. So what I want you to do is this. I want you to pause the video, and I want you to try to think of what are the 4 easiest numbers to plug in for x. Think about what we talked about what you want to make the bars. I want you to take those 4 numbers. I want you to plug them in. I want you to make the graph, okay? Then what I want you to do after you pause the video, found those numbers, attempted the graph, I want you to unpause and see if you and me ended up getting the same thing. All right, so what I would start by doing, is I would start by plugging in 2. I want to make the bars equal to 0. That's where, and again, people really get confused about the signs. Like, what does it mean if it was a positive number instead of a negative number? Like, they get with like the flipping the signs, and people try to teach all these rules about when the sign's positive, do this, when it's negative, do this. I don't get caught up in that. What I want to think about is make the bars equal to 0. And if you can just focus on that instead of the signs and those rules, 1, you're going to get the right answer. But 2, again, when we get to other scenarios that look like this, that's not going to be something that holds you back. Okay, you're not going to have to memorize these rules. So 2 makes the bars equal to 0. So I'm going to plug in 2. So I'm going to get 2 minus 2 in the bars plus 3. 2 minus 2 is 0. The absolute value of 0 is 0. And 0 plus 3 is 3. So 2 is a number you definitely want to plug in. Now, I know a lot of people do 1, 2, 3, 4. And you know, look, if you did, you'd be right. But again, we want to start thinking about getting away from 1, 2, 3, 4, 5, right? Again, very tempting to do it, but we want to start thinking about, again, how we can be strategically choosing these inputs. So the next input I would personally choose is 3. Why would I do that? Because I want to make the number in the bars relatively small. I think I might have shifted everything. I don't know. So, all right. So what I'm going to do is I'm not going to do x. What I'm going to do is, where's my pen? I'm going to do, let's go, 3 minus 2 plus 3. It makes the numbers in the bars, that is, as small as possible. So I get 1. And again, my pen sometimes just wants to do whatever it wants. It doesn't really always care about what I have to say. See, it's starting to, oh, I don't know why it does that. Let's try it one more time. All right, absolute value of 1 plus 3. The absolute value of 1 is 1. 1 plus 3 is 4. Okay, so we have 3, 4. Okay, where can we go from there? I don't know. Well, let's try 4. I mean, again, not that we want to be going 1, 2, 3, 4, but 4 gives you a nice number in the bar. So that was 1. If I do 4, I'll do that off to the side. I get 4 minus 2 in the bars plus 3. 4 minus 2 is 2. So it's the absolute value of 2 plus 3. The absolute value of 2 is 2. 2 plus 3 is going to give me 5. All right. Last but not least, I'm sorry, that was not 1. My apologies. That was 3. That gave me 1. Last but not least, I am going to try 1. Why would I try 1? Well, 1, when you plug it in, gives you the same thing as -1. So I'm just going to erase this just so I have some room. So when I plug in 1, here's what I get. I get 1 minus 2. But the thing is, inside of the bars, what that gives me is -1. And -1 has the same absolute value as +1. It's 1. So I get 1 plus 3, which is again 4. So what you really want to do is you really want to get in the habit of thinking about what's going on here. Well, what we have is this really, really nice symmetry that we can use to our advantage to help take what might seem like a hard problem and break down some of those barriers by thinking about how can we use the symmetry to actually do a lot more with relatively less. Okay, now again, I'm going to do a little bit of analysis here. I'm going to go ahead and grab this and I'm going to move it up. Let me get this graph up and think about how did the graph change between the blue and the purple. I went to the right by 2. Notice the right, -2 moved me to the right, whereas in the previous graph, I moved to the left and I moved up 3. So as with exponential functions, the +3 moved me up, which is what I would expect. And the -2 in the bars did the opposite. So you'd think that the -2 would move you to the right, or you think, sorry, that it would move you to the left because the negatives are on the left, but it actually moves you to the right. All right, guys, last one. I want to be clear what we're doing here, and this might have gotten cut off. So I'm going to do the absolute value of, I'm going to do -2 times the absolute value. I'm going to rewrite it if you need me to. I'm going to put a -2 on the outside. So what I want you to do again, think of those 4 easiest numbers to plug in for X. Then what I want you to do is pause the video, plug in those 4 nice numbers, make your graph, and then when you're ready, unpause and see if we got the same thing. All right, so hopefully you're following along with me. What we're going to do is we're going to use -3 as the first X value, because when I plug in -3, what I get inside the bars is 0, and we want the bars to be equal to 0. So I get -2 times 0, or 0. Okay, then I'm going to plug in. You don't want to plug in a number that's too big. So I want to make the bars equal to 1, right? 1's a nice small number. So what's going to make the bars equal to 1? I could plug in -4. All right, I got to be really careful because my pen is going to act up on me. I don't want that to happen. So -4 plus 3, that's going to give me -1. What's the absolute value of -1? It's 1. And -2 times 1 is -2. Now, if you didn't plug in -4 right away, that's okay. But notice, what am I doing? I'm plugging in numbers that are close to the vertex. So I'm going to go 1 to the right of the vertex, 1 to the left of the vertex. You don't have to plug in that many points, because once you just have a couple and the vertex, you can go from there. And that's what makes the vertex all the more important. Okay, now I'm going to plug in -2. -2 plus 3. Okay, -2 plus 3 is 1. The absolute value of 1 is 1. -2 times 1 is -2. Boom. Boom. Okay, one more. I'm going to go -1. Now, which y value would have the same, which x value would have the same y value? Think about the symmetry here. What x value would have the same y value as -1? The answer would be -5. So if you plug in -5 and -1, you would get the exact same thing. So I'm going to plug in -1 because I want to work with smaller numbers whenever possible. Okay, so again, think about these strategies. Okay, so -2, so that becomes 1 plus 3 is 2. The absolute value of 2 is 2, and -2 times 2, -4. So -1, -4. All righty, all right. Let's go ahead and do my graph. Down like that, down like that, and we have ourselves a graph, folks. So again, a couple things. Let's go ahead and do one last comparison. So I'm going to slide this on up. So a few things happened here. One, it shifted to the left, but notice how it also was reflected over the x-axis, okay, making it point down, and it's also stretched vertically. See how the graph's a lot more narrow? So the -2 on the outside of the bars, the negative caused the flip, because what it does is it takes the y values and it flips their signs. And when you flip the signs of the y value, now you flip to being below the x-axis, because that's where the negative y values are. The 2 takes all the y values and it doubles them. What they were supposed to be, it doubles them. And when you double them, that's going to have the effect of stretching vertically, because now the y values are twice what they were before. All right, folks, so hopefully you found this to be helpful. Again, as a recap, what have we done? One, we've talked about what is absolute value and what is an absolute value function. Definitely stuff you want to have right now. Next thing we talked about is 4 quick examples of graphing and making tables of absolute value functions, where we're thinking about making the bars 0 and setting up nice, easy numbers within the bars so we can plot and build a graph really quick, but also really accurately. As we go forward, do not do anything with this now. We're going to be looking at absolute value equations, and as we do so, we're going to start by looking at them both geometrically and algebraically, and then we're going to transition to probably more doing some stuff algebraically. All right, folks, so again, hopefully you found this video to be helpful. Thank you so much for watching. Have a wonderful day. Don't ever forget to love math, and remember, you can do it. All right, guys, thanks again. Until next time, have a wonderful, wonderful day.